In this contribution, we present a novel, physically accurate approach for the simulation of weather. Our model supports a wide range of cloud and precipitation types, as well as heat transfer in the environment, which allows us to simulate complex weather phenomena. Our approach is able to simulate 3 cloud species: warm clouds made up of condensed water droplets, cold clouds which are composed of ice crystals, and mixed phase clouds in which both supercooled water droplets and ice coexist. Multi-layer clouds, for example, emerge as a result of cold cloud formation in the upper atmosphere and warm cloud formation in the lower atmosphere. Mammatus clouds are formed due to differential warming in the base of the cloud, which produces a convective overturn. A trigger for nucleation, such as atmospheric instabilities or a plane flying through the cloud, causes alto cumulus clouds made up of supercooled water to quickly evaporate due to the Bergeron process, leaving a hole in the cloud. Our novel water phase transport scheme allows us to model different precipitation types. In these scenes, we demonstrate the simulation of light rain in the Appalachian Mountains, a snowstorm over the Popocatépetl volcano, and heavy snowfall in the Yosemite National Park. Here we show the temporal evolution of a developing cumulonimbus cloud, emerging from cumulus clouds generated with the classical Kessler water phase transport model on the left side, and with our extended microphysics scheme on the right side. The inclusion of ice phase transitions and their corresponding thermodynamics in our model results in additional buoyancy that allows to more realistically simulate the formation of these types of clouds. We account for daily temperature changes as well as heat transfer between pedosphere and atmosphere, allowing us to simulate complex weather effects. In this scene, we demonstrate the evolution of cloud formations passing by a topographic barrier, without atmospheric heat transfer and with atmospheric heat transfer. The inclusion of heat transfer in the atmosphere allows us to recreate the so-called Foehn effect. The resulting temperature gradient blocks incoming clouds and results in a Foehn wall. Our approach simulates the motion of water from the ground to the atmosphere and back again, which is called the hydraulic cycle. Here we initialize our simulation with a heavy storm on the top of the mountain at night. Rainwater is transported down the mountain and able to infiltrate the ground. On the upper right side, we visualize the corresponding subsurface water map. As day progresses, this water content in the ground is evaporated back to the atmosphere and condenses back into the clouds. Finally, we show different weatherscapes simulated by our framework. In this scene, a cloudy morning at the coast of Yucatan develops during the day, resulting in a warm, cloudy night in the land. Here, different cloud patterns develop from the morning until the night in the Swiss Alps. In this scene of the Sahara Desert, the air does not contain enough water vapor content to create clouds. This results in a very hot temperature during the day as there are no clouds, which could attenuate incoming solar radiation. After subsurface water has evaporated, small clouds appear in the afternoon and continue developing during the night. Thank you for your interest in our work and watching this video. The corresponding publication and supplemental material, as well as more information about the authors and our research, can be found on the project website.